Hi guys, let's re-brush up on those long forgotten concepts of algebra, some of the formal rules. And we'll begin by just saying that algebra is nothing more than making something look like something else. Symbol manipulation, if you will. Now, that's a bit of an oversimplification of what algebra is, but for now it will suffice, and we'll get into those long forgotten concepts that we once dreaded. And this is just a recap, and I highly encourage everybody to get a piece of paper, get a pen, and manually do all this stuff whilst reading it out aloud. Mathematics is largely mechanical, and to reinforce some of those concepts, we need to do the mechanics of it, which for a lot of people, unfortunately, means getting that pen out. So let's begin. Right, so I'm just going to zoom in, make things a little bit clearer. I'm going to scroll down. I'm going to get right into the meat and gravy of this topic, and I'm going to begin with one of the first rules of algebra. So when we have a number, if we multiply that number by 1, we still retain that number. So for example, 1 times any number is still that number. So in this case, that number is represented by the symbol A. And if we say 1 times A, we still get A. We don't change A. So 1 times any number does not change that number. And incidentally, it's called the identity of multiplication, but for the purposes of this tutorial, that's not that important. What is important is you remember that when we multiply any number by 1, the number just does not change. And here we have some examples of this property. And if we multiply A by -1, we still retain that negative number. And if we remember, if we dig deep into our memory banks from yesteryear, you'll remember that when we have two like signs, we have a positive, and therefore an implied one is existing here. And when we multiply that implied one by A, we still get A. This is just reiterating this property. And if we look here, if we have something of this form, we can rewrite it as this form. So A plus negative B is equal to A minus B. So when we see something what looks like this, whether it's x plus negative y or an elephant plus negative an elephant, then we can rewrite it in this form. And that's all that is. And similarly, we can rewrite this in this form. If you remember again, a negative multiplied by a negative produces a positive. So we can rewrite this as A plus B. Let's take a look at the rule of symmetry. This is quite an important rule. So when we have this blue box here, this is a formal rule. So what we're saying is if A is equal to B, then B is equal to A. And it makes sense. So if this equals this, then this must equal this. They must be the same thing. Quite simple concept to get your head round. But again, sometimes when we're doing these things when we're doing the mechanics of these things on pen and paper, and we're not really being descriptive in plain prose and describing things in plain and easy language, then sometimes these concepts don't have much meaning. But if we say that something equals something, then this and this must be the same thing. So for one thing, this means that a rule of algebra goes both ways, since we may write P plus negative Q as P minus Q. Remember here, we rewrote the form of this, A plus negative something as A minus B. So we just rewrote or rephrase that particular rule. And that is in a calculation, we may replace P plus negative Q with P minus Q. Then symmetrically, this is important, P minus Q equals P plus negative Q. So we go back to where we started. We may replace P minus Q with P plus negative Q. So this equals this. The rule of symmetry also means that in any equation, we may change the sides if, for example, 15 equals 2x plus 7, then we are allowed to write 2x plus 7 equals 15. So we've moved this across here and we've moved this across here. And so the rules of algebra tell us what we are allowed to write. They tell us what is legal. So as you can see, all we've done is move that over that side of the equal sign and the 15 over the other side. So what this is saying is this equals this, whatever this may be. But we know what this is. It's 15. And we know that this whole expression here is also 15. Right, so problem time. Let's run through a few problems. We're going to use the rule of symmetry to rewrite each of the following, and note that the symmetric version is also a rule of algebra. So what do we have here? We have 1 times x. That's the identity of multiplication. 1 times x does not change x. So therefore x is just x equals x. And for the rule of symmetry, we transpose this over here and we transpose this over here, which does not break the rule of symmetry. And it just means that x equals 1x. And similarly here, we have the rule of identity, the identity of multiplication rule. And we have negative x on this side. If we transpose these to the other sides, we get negative x equals negative 1x. If you remember, x plus 0 does not change x. Adding 0 to a number does not change that number either. And if we look at the rule of symmetry, we are just flipping sides. And this is getting a little bit tedious, so we're going to move on to the commutative rules of algebra. So let's look at the word commutative. Think of the word commute. When we commute, we go from point A to point B. Some days that might be different, but ultimately we are traveling from some location to another location. And similar with the commutative rule of addition, the order in which we write terms will not affect the sum. So we can have one term and another term, and we can flip these terms, and the ordering does not affect the sum. This still equals this. And if you remember the rule of symmetry, if this equals this, then we can flip or transpose these whole terms over to this side, and similarly we can do the same thing here. So the ordering of terms will not affect the sum. And why do we know this is a sum? Well, we have one term, and the mathematical operation of addition separates those terms, and thus that is what constitutes a sum. So that, in a nutshell, is the commutative rule of addition, and we can expand all those terms out into the infinite mass of the universe. We can go as many terms as we want. So as you see here, we have one term, two terms, three terms. Incidentally, this is positive b, and there is an implied plus negative sum, and that is why it's called a sum, even though we are dealing with the subtraction. We have an implied plus here, and if we look, the ordering of terms does not matter. We can spell out various words with these terms, and if you look, we have a term here, a term here, a term here, and a term here. So the order does not matter. Right, so let's move on to an example. So it says apply the commutative rule to P minus Q. Remember the commutative rule. Let's go back up. So the order in which we write terms will not affect the sum. That is the commutative rule. So let's just do a recap of that, and then we're going to apply this solution. The commutative rule for addition is stated for the operation add. Here, though, we have the operation subtract, but we can write P minus Q equals P plus negative Q. These are both sums. This one is clearly a sum. We have the first term, we have the second term, and confusingly, this is also a sum because there is an implied plus just about here. As you can see, it is here. So what we are doing is we are rewriting this form in this form, but they are both the same thing. We are still talking about sums, even though here we are subtracting. So I hope that's clear, and therefore p minus q equals negative q plus p. This is the commutative rule of addition. What we have done is we have reordered the terms, and we've put this to the left of p, and we've moved p over to the right. This is quite difficult to express verbosely in plain prose, because I ideally would need a pen, but hopefully this is getting through. Let's move on to the commutative rule of multiplication. So here's another formal rule inside the blue box, and it says that the order of factors does not matter. So let's say we have two factors here, a and b, and two factors here, b and a. And how do we know that they are factors? Well, they are buttered up to each other, and there is an implied multiplication symbol here. Similarly, there is an implied multiplication symbol here. So the order of factors does not matter. This is the commutative rule of multiplication. And if you can see here, we have four distinct factors, a, b, c, and d. And we can rearrange the ordering of those factors, and the result will still be the same. So here we say the rule applies to any number of factors. You can imagine this going out infinitely to the right, and it could go infinitely to the left. It doesn't matter. What is more, we may associate factors in any way, so we can group the factors. Here we have a single factor, and inside that factor we have three distinct factors, and we're multiplying this whole factor here by this factor, and similarly we are reordering things here. So in essence, the order of factors does not matter. Let's move on to an example to spice things up a bit. Let's scroll up, and we are saying multiply 2x by 3y by 5z. This raised dot represents multiplication, and we use a raised dot for multiplication in algebra so as not to confuse an x with a multiplication symbol. Right, so multiply 2x by 3y by 5z. Solution, let's see the solution. The problem means multiply the numbers and rewrite the letters. So if you remember the commutative rule of multiplication, the order of factors does not matter. We can butt this up to this, in any particular order we feel will help us solve this problem better. So if we look at this particular solution, we've multiplied the 2 by the 3 by the 5. And we've put them together, the factors are together, and we've grouped the x, y, and z. So if we multiply 2 by 5 to get 10, and then multiply 10 by 3 to get 30, as you can see here, we've just placed those factors together to rearrange things into a more suitable manner so that calculations are easier. So if we look here, it says it is the style in algebra to write the numerical factor to the left of the literal factors. So what does that mean? In a nutshell, it just means let's write the numbers before the letters. It's that simple. This is just a fancy way of saying that. So let's do a few problems. Let's multiply 3x by 5y. So let's first multiply 3 by 5, which is 15. And then we're left with x and y. So that would be 15 times x times y. And we can write that as 15xy. So here is a factor. Here is another factor. Here is another factor. And we've got 7p times 6q. 7 times 6 is 42. And then we've got p and q, 42pq. Let's do 3a multiplied by 4b multiplied by 5c. Now let's do the numbers first. So I'm going to go 4 times 5, which is 20. And then I'm going to do 20 times 3, which is 60. And we're left with A, B, C. Or you could do 3 times 4, which is 12. And 12 times 5, which is 60. And then we could have A, B, C. We could also have C, A, B. But it's more common notation to order the literal variables in alphabetical order. So we have 60, A, B, C. And we're going to move on to problem 3. Rewrite each expression by applying a commutative rule. Problem 3. Rewrite each expression by applying a commutative rule. So what rule are we going to apply to this? We are dealing with sums, so it makes sense that we're going to use the commutative rule of addition. So negative p plus q, what we're going to do to this, I'm just going to hover over this, and we can see all we've done is reorder this term with this term to produce q plus negative p. In other words, q plus negative p is the same thing as q minus p. B, so we've got 2 factors, so let's think about the commutative rule of multiplication. And we've got 2 factors, and if you remember back, the order of factors does not matter, so we can move this to the right of 6 here, and we get 6 multiplied by negative 1. And here we have x minus 2 is one term, and we have x plus 1 as the second term, and here we're going to use the commutative rule of addition to reorder the terms, and we have x plus 1 plus x minus 2. And here we have 2 factors, factor 1 and factor 2. Inside this factor are these grouping symbols which denote a group. We have 2 terms. This is a term, this is one term, and this is the next term. Sorry, this is the next term. And just because we are talking about subtractions does not mean we are not dealing with sums. This is x plus negative 2. It's an implied plus. Here we have a clear x, add 1, 2 terms, and 2 factors. And what we're going to do is we're going to move this whole group to this side of this group.